In Chapter 3, we are going to continue our discussion of functions. In Section 3.1, we are going to look at quadratic functions. In Section 3.2, we're going to look at general polynomial functions and what their graphs look like. In Section 3.3, we're going to divide polynomials and get the remainder and factor theorems. In Section 3.4, we're going to find the zeros of polynomial functions. In Section 3.5, we're going to introduce rational functions and what their graphs look like. And in Section 3.6, we'll do polynomial and rational inequalities. In Section 3.1, we are going to look at quadratic functions. Our objectives are to 1, recognize the characteristics of parabolas. 2, graph parabolas. 3, determine a quadratic function's minimum or maximum value. 4, solve problems involving a quadratic function's minimum or maximum value. What is a quadratic function? A quadratic function is any function in the form f of x equals ax squared plus bx plus c, where a, b, and c are real numbers and a cannot equal 0. A quadratic function is a polynomial function whose greatest exponent is 2. The graph of a quadratic function. The graph of any quadratic function, f of x equals ax squared plus bx plus c, is called a parabola. If the coefficient of the x squared, a, is a positive number, the parabola opens upward. If the coefficient of x squared, a, is a negative number, the parabola opens downward. The vertex, the turning point of your parabola, so where your parabola changes direction, is the lowest point on the graph when the parabola opens upward. It's the highest point when it opens downward. Parabolas are symmetric with respect to a vertical line that goes through the vertex. That is called the axis of symmetry. If you take a parabola and you fold it along that axis of symmetry, the two halves of the parabola will meet exactly. The graph on the left here is an example of a parabola that opens upward. So the coefficient a on the x squared is a positive number. It has an axis of symmetry, a vertical axis of symmetry that goes through the vertex. And since it's a parabola that opens upward, it has a minimum value. And that minimum point occurs at the vertex. The graph on the right is an example of a parabola that opens downward. So the coefficient a on the x squared is a negative number. It also has a vertical axis of symmetry that goes through the vertex. Since it opens downward, it has a maximum value, and that maximum value occurs at the vertex. In Section 2.5, we looked at the 7 standard functions. And one of our standard functions was the standard quadratic function, f of x equals x squared. And we did various things to transform that function. We shifted it left and right. We shifted it vertically up and down. We multiplied it by constants greater than 1 to stretch it. We multiplied it by constants between 0 and 1 to shrink it. The graph of the standard quadratic function is the graph of a parabola whose vertex is at the origin. In this figure, we have a parabola whose coefficient A is a positive number, so it opens upward, and we've transformed that function. The graph in black, that's graphed in black, is f of x equals ax squared, where a is positive, and it can be some number that either stretches or shrinks the graph. Now, to move this graph, transform it horizontally and vertically, we do two things. If we subtract a constant from the input of our function x, that has the effect of shifting the function that many units to the right. So if we take our quadratic function f of x equals ax squared, and we subtract some number h from the x, that will shift the function h units to the right. If we take some number k and we add that to the output of the function f of x equals ax squared, so we add some number k to the output, that has the effect of shifting the graph of our function up. So when we add the k, that is going to shift our graph k units up. This is the same idea. We're just looking at it now for a parabola that opens downward. So in this case, if we have the standard function f of x equals ax squared, then a is a negative number, which causes the parabola to open down. But again, we're taking some constant h and we're subtracting it from the input of x. And we're taking some number k and we're adding that to the output of f of x. So when we subtract a number from the x and we add a number to the output, that has the effect of shifting the parabola h units to the right and k units up. So what you've done in both of these examples is you've moved the vertex. You've taken the vertex of f of x equals ax squared and shifted it h units to the right and k units up. So you've moved the vertex to hk. The axis of symmetry of the standard quadratic function is the y-axis. When I shift that graph h units to the right, I've shifted the axis of symmetry h units to the right. So the axis of symmetry's equation will be x equals h. These figures show the graph of g of x equals a times x minus h squared plus k in blue. You can compare those two graphs to the original standard quadratic function, f of x equals ax squared. And you can observe that h determines a horizontal shift, k a vertical shift in the graph of f of x equals ax squared. So this form, f of x equals a times x minus h squared plus k, is called standard form. I can look at the equation of the quadratic function when it's in this form, and I can determine the vertex of that parabola. The vertex is, the first coordinate of that vertex, h, is the number I'm subtracting from x. The number k, what I'm adding to the output, is the vertical shift. That's going to be the y component of my vertex. So my vertex will be the point hk. The parabola is symmetric with respect to the line x equals h. If a is greater than 0, it opens upward. If a is less than 0, it opens downward. So we can now use this information to graph a parabola when its equation is in standard form. To graph f of x equals a times x minus h plus k, a cannot equal 0, otherwise it's not a parabola. Determine whether the parabola opens upward or downward. If a is positive, greater than 0, it opens upward. If a is negative, less than 0, it opens downward. Determine the vertex. The vertex is the point hk. Find any x-intercepts by setting the function equal to 0. Remember, if it's an x-intercept, that means the value of the function y is equal to 0. If you're on the x-axis, y is equal to 0. The function's real zeros are the x-intercepts. So when you set the function equal to 0 and solve the quadratic equation, the real number solutions to that equation are x-intercepts. You find the y-intercept by evaluating the function at 0. Remember, if you're on the y-axis, x is equal to 0. So we can find the y-intercept by evaluating the function at x equals 0. Then you plot the intercepts, the vertex, any additional points as necessary, connect the points with a nice smooth curve that's shaped like a bowl that opens up or an inverted bowl that opens down. All right, so let's graph this quadratic function. We have f of x equals negative x minus 1 squared plus 4. Step 1 is to determine how the parabola opens. Does it open up or does it open down? Since I have a negative outside the parentheses, x minus 1 squared, that means that that coefficient a is a negative number. As a matter of fact, a is equal to negative 1. Since a is negative, that means the parabola opens down. So it's going to look like this. The second step is to find the vertex. Whatever number I'm subtracting from x, that is the first component of my vertex. So in this case h is 1. The y component of my vertex is whatever I'm adding or subtracting from the output. Since I'm adding 4, the y component is 4. Again, if we look at this with respect to how we shift the graph, subtracting 1 from the input shifts the graph to the right. Adding 4 to the output shifts it up. So we are moving the vertex from 0, 0. We're moving it 1 unit to the right and 4 units up. So we're going to shift the vertex to 1, 4. The next thing we need to do is find the x-intercepts, if there are any. We find the x-intercepts by setting the function equal to 0. So we take our function and we set it equal to 0 and we solve the resulting quadratic equation. Probably the easiest way to solve this quadratic equation when the quadratic function is in standard form is to use the square root property. You could certainly multiply this out and use the quadratic formula or factoring if you wanted to. It's just faster, in my opinion, to use the square root property. So I'm going to subtract 4 from both sides. And yes, I could add the negative x minus 1 squared to both sides. I'm just going to do it this way. I am going to divide by negative 1 because I don't want those negatives on both sides. And when I divide by negative 1, the negatives will cancel and I'll end up with a positive. All right, I'm going to take the square root of both sides. And remember, when I take the square root over there on the right-hand side, I need to put the plus or minus in front of the square root. There are two numbers that I can square and get 4, 2, and negative 2. All right, so x minus 1 is either equal to negative 2 or x minus 1 is equal to positive 2. Add 1 here. So either x is equal to negative 1 or add 1 here. X is 3. So our two x-intercepts are at negative 1 and positive 3. The next thing we do is find the y-intercept by computing f at 0. So we're going to evaluate our function at 0. Zero minus 1 is minus 1. When I square negative 1, I get positive 1. So this is negative 1 plus 4, which is 3. So now I have my y-intercept. This is what we know. We know that the parabola opens down because the coefficient a was a negative 1. We know the intercepts, the x-intercepts are at 3 and negative 1. We know the y-intercept is 3. We know the vertex is at 1, 4. So now I can plot all these points and connect them using a smooth curve. So the vertex is at 1, 4. The y-intercept is at 3. The x-intercepts are at negative 1 and 3. And I could connect these points using a smooth curve. So that is what the graph of this parabola looks like. Let's graph another one. We're going to graph f of x equals x plus 3 squared minus 1. So let's first determine whether the parabola opens up or down. The coefficient a on the x squared is the number 1. We have an understood 1 sitting right there. So a is 1. That is a positive number, so it opens up. The vertex. All right, so what effect does adding the 3 to the input have? How does that shift the graph of the standard quadratic? Remember, adding 3 shifts the graph to the left. So this takes the vertex that is at 0, 0 and shifts it to the left to negative 3. So the x component of my vertex is negative 3. Again, the x component of the vertex is whatever number I'm subtracting from x. So I could write this as x minus a minus 3 squared. I'm subtracting negative 3, so the x component of my vertex is negative 3. Or you can look at it in terms of a transformation. Adding 3 to the input x has the effect of shifting it to the left 3 units. So the vertex is going to be at negative 3. I'm also subtracting 1 from the output. The number k is whatever that value is. Is it positive or negative? If it's positive, it shifts up. If it's negative, it shifts down. So the y component of my vertex is just whatever this number is right here. That's k. So k is equal to negative 1. And just looking at that, I do know that the transformation is that I'm shifting to the left 3 and down 1. Find the x-intercepts by solving f of x equals 0. So I have f of x equals x plus 3 squared minus 1. I'm going to set that equal to 0. And again, probably the easiest way to solve a quadratic equation like this is to use the square root property. So I'm going to add 1 to both sides. take the square root of both sides, and I have to put the plus or minus over on the right-hand side. The square root of 1 is 1. So I have x plus 3 is equal to -1, or x plus 3 is equal to +1. Subtract 3 from both sides here. X equals -4, so there's one x-intercept. Subtract 3 here. 1 minus 3 is -2. So there are my two x-intercepts. To find the y-intercept, we evaluate the function at 0. Three squared is 9. 9 minus 1 is 8. So now we have all the information we need to graph this. The parabola opens upward. The x-intercepts are -4 and -2. The y-intercept is at 8. The vertex is at -3, -1. And what I didn't do on the previous example, which I should have, is draw the axis of symmetry and label that. Remember, the axis of symmetry is a vertical line that bisects the parabola. It goes through the vertex. So that equation would be x is equal to -3. A vertical line has an equation, x equals a constant. All right, let's plot the rest of these. We have a x-intercept at -2 and one at -4. And we have a y-intercept that's off my graph here, up here at 8. And we can draw. And to show you how this axis of symmetry works for you, if I have a point here at 0, 8, which is 3 units away from the vertex, I will have a point 3 units away the other direction from my vertex at -6, 8. Because the parabola is symmetric about that value, you can actually find another point on the graph of your parabola by using its symmetry. So again, if I have a point that's 3 units to the right of my vertex at 8, I will also have a point 3 units to the left of my vertex at 8. So I'm going to have a point that's symmetric to 0, 8 at -6, 8. All right, and it looks like we have a little problem with the slide here. Had some operation symbols go missing on us. All right, let's consider a parabola whose equation is in this form here. F of x equals ax squared plus bx plus c. How do you find the vertex when it's in that form? When it's in standard form, you can just look at the equation and determine the vertex by the transformation that's occurred. But if it's not in this form, we actually have a formula that helps us find the vertex. And the formula is that the x-coordinate of the vertex may be found by taking b, a coefficient on the x term, and dividing it by 2 times a being the coefficient on the x squared term. And then you change the sign of that. So the x-coordinate of the vertex is -b over 2a. Now, how do you find the y component of your vertex? Well, you evaluate the function at that value of x, whatever it is. You plug that back into the function, and that'll give you the y value of your vertex. So to find the x value, you use the formula -b over 2a. To find the y value, substitute that value in for your input x, evaluate the function, and that will give you y. Still have our missing operation symbols here. Put those back in. So to graph a parabola that's in this form, Again, you determine whether it opens up or down by looking at the number A. If it's positive, it opens up. If it's negative, it opens down. Then you find the vertex. You find the vertex using the formula. The x component of the vertex is minus b over 2a. The y component of the vertex is the function evaluated at that point. Find any x-intercepts by solving the equation f of x equals 0. The y-intercept is probably the easiest thing to do here, because to find the y-intercept, you let x equal 0, you evaluate the function at 0. But if you let x equals 0, the x squared goes away. The x goes away. So all you're left with is c. So when your quadratic function is in this form, the constant is your y-intercept. Plot the intercepts, the vertex, any additional points as necessary. Connect these points with a smooth curve. All right, so let's graph a function that's in the form f of x equals minus x squared plus 4x plus 1. So let's graph this when it's in this form. All right, does the parabola open up or down? Well, the coefficient on the x squared is -1. So this thing opens down. Now, to find the vertex. Well, I can't just look at this and determine the vertex. I'm going to have to use the formula. It's not in standard form, so I can't just determine what h and k are. I'm going to have to use the formula. So I need to know what a and b are. So a is -1. We've already established that. And b is the coefficient on my x term. So b is 4. So to find the x coordinate of my vertex, it's minus b over 2a. So I have minus 4 over 2 times minus 1. So I have minus 4 over minus 2. Minus gives me plus. So the x coordinate of my vertex is the number 2. Now to find the y coordinate of my vertex, I actually have to evaluate the function at 2. So the y coordinate is f evaluated at 2. So I plug that in, and I get minus 4 plus 8 plus 1, which I believe is 5. So the vertex of this parabola is at the point 2, 5. All right, so next I'm going to look for the x-intercepts. And I already found the vertex. We're going to look for the x-intercepts. And we find the x-intercepts by setting this function equal to 0. And that's not factorable. So I'm going to have to use the quadratic formula. Minus b plus or minus the square root of b squared minus 4 times a times c, the whole thing over 2a. All right, so I have x equals minus 4, b is 4, c is 1, a is -1, plus or minus the square root of 4 squared minus 4 times a is -1, c is +1, all over 2 times -1. So x equals -4 plus or minus the square root of 16 plus 4, that would be 20, over -2. And that's going to be some irrational number. So I think that the best thing for me to do at this point is take my calculator out and get 2 decimal approximations to this. So the first decimal approximation would be found by taking -4 minus the square root of 20 and dividing that by -2. So take your calculator out and do that calculation, and I get 4.24 approximately. The other approximation would be found by taking -4 plus the square root of 20 and dividing that by -2. So take your calculator out, take -4 plus the square root of 20 and divide that by -2. And when I do that, I get x is approximately -0.24. So there's my two approximations for my x-intercepts. And that's okay that I'm just getting an approximation because I'm going to plot that on the x-axis as best I can. Right, to find the y-intercept is f of 0. F of 0 will be 1. It's going to be the constant. So now I have all the information that I need to graph this function. Okay, the vertex is at 2, 5. The x-intercepts, I have one at -0.2, oh, maybe about right there. One at 4.2, maybe about right there. The y-intercept is at 1, and we have an axis of symmetry that bisects my parabola, goes right down the middle of it. So if I wanted to, I could find, using symmetry, if I have a y-intercept right there, then I'm going to have a point right there. If I have a point that's 2 units to the left of my axis of symmetry, I will have a corresponding point 2 units to the right. And now we can connect these points using a smooth graph. Still missing those operation symbols in that quadratic function. Okay, so considering this function, if the coefficient a on the x squared is a positive number, that means the parabola opens up and it has a minimum at its vertex. So it has a minimum that occurs at x equals -b/2a, and the minimum value of that function is its y value. So it's the y coordinate of the vertex. So the minimum is the y coordinate of the vertex, and it occurs at the x coordinate of the vertex. If a is less than 0, it's a negative number, then the function has a maximum. And that maximum occurs at the vertex. It occurs at x equals -b/2a, and its maximum value is the function evaluated at that value. In each case, the value of x equals -b/2a gives the location of the minimum or maximum value. The value of y, f at -b/2a, gives that minimum or maximum value. So minimum or maximum values are y values, and they occur at some x. Okay, so let's consider this quadratic function. Determine, without graphing it, whether the function has a minimum value or a maximum value. In this function, the coefficient on the x squared term is 4. A is 4. That is a positive number. Since this is a positive number, this parabola opens up. Since it opens up, it has a minimum. All right, so what is that minimum value? To be able to determine that minimum value, I need to find the vertex. Okay, so we're going to find the vertex. The x coordinate of my vertex is -b/2a. Okay, so b is -16, a is 4. So let's make those substitutions. Minus a minus over 2 times 4 is 16/8, which is 2. So that's where the minimum occurs. What's the minimum value? Well, the minimum value is this function evaluated at 2. So I'll find f of 2. Take your calculator out and do this calculation. And I find this to be 984. So the minimum is 984 and it occurs at x equals 2. So we have a minimum value of 984 at x equals 2. All right, so now let's determine the domain and range. Identify this function's domain and range without graphing it. I was about to draw a graph. Can I do it without drawing a graph? All right, so since this opens up and its vertex is at 2, 984, since it opens up, I know that this is a minimum point. Since it's a minimum point, I know the graph of this function starts there and goes on forever in the vertical direction. So the range is from 984 to infinity. So the range starts at that minimum value and continues on forever. The domain of every quadratic function in existence, unless stated otherwise, the domain is the set of all real numbers. There's no number you can't plug into this function. No real number. There's no real number you can't square it and multiply it times 4 and then subtract 16 times it and add 1,000. So the domain of this quadratic function into every quadratic function, unless stated otherwise, is the set of all real numbers. Now, what if you had a parabola that opened down? If it opens down, then you have a maximum. Sorry about that. We had a PowerPoint failure. Right, back to my slide. So if it opens down, you have a maximum value. So what's the range? Let's call this K. Well, the range will start at negative infinity and it will end at whatever that maximum value is. So if the parabola opens up, the range starts at the vertex and goes to infinity. If the parabola opens down, the range starts at negative infinity and ends at that vertex. You always use a bracket next to the number, the y value of the vertex, because that point is on the graph of the vertex, the parabola. So if your parabola opens up, your range is going to be from whatever that y value of the vertex is to infinity. If it opens down, it's going to be from negative infinity to whatever that y value of the vertex is. All right, solving problems using maximizing or minimizing. Read the problem carefully and decide which quantity is to be maximized or minimized. Use the conditions of the problem to express the quantity as a function in one variable. Rewrite the function in the form f of x equals ax squared plus bx plus c. Calculate the x component of the vertex. If a is greater than 0, then the function has a minimum at that point, and the minimum value is the function evaluated at that x value. If a is less than 0, it has a maximum at the vertex. The maximum value is the function evaluated at that value, and then answer the question posed in the problem. All right, so let's look at an example. So what we want to do here is maximize the area of an enclosed area. You have 100 yards of fencing to enclose a rectangular region. Find the dimensions of the rectangle that maximize the enclosed area. So they tell you what you're going to maximize. What is the maximum area? So this problem's pretty transparent. decide what must be maximized or minimized. Well, they're telling you, we want to maximize the area of this enclosed yard. So what are we maximizing? We're maximizing the area. And that disappeared from the slide. Okay, we're going to take just a second here, and we're going to restart PowerPoint and see if that helps. Okay, so what are we wanting to maximize? We are wanting to maximize area. Yeah, that's better. Okay, so then let's express this quantity area as a function in one variable. So we know from geometry that the area of a rectangle can be found by multiplying its length times its width. So if I call this x and I call this y, then I know the area, which is what I'm trying to maximize, is equal to x times y. All right, we were given another piece of information in this problem description. We are told that we have 100 yards of fencing. So what's that mean? Well, that means we can enclose this area with that 100 yards of fencing. So how do we measure the enclosed length of a rectangle? Well, it's called the perimeter. So the perimeter, which we know we have a formula, 2x plus 2y, that's equal to 100. That's how much fencing I have to fence in this area. Now, I might, if it were me, and it's me since I'm the one doing this problem, I might divide both sides of that perimeter equation by 2 just to make it a little bit easier for me to deal with. And I can do that since I have common factors of 2 in every single term on both sides of the equation. I can divide everything by 2. 100 divided by 2 is 50. Oh, and she left the 2 in on the y. Better erase that one. There we go. That's better. Okay, so now I know the perimeter is x plus y equals 50, and the area is xy. So now I can write the area in terms of one of my variables. If I take the perimeter equation, for example, and subtract the x from both sides. So y is 50 minus x. So now I could write the area of this enclosed area here as x times 50 minus x. And that is what I am trying to maximize. I'm trying to maximize that x times 50 minus x. Okay, so how do I find that value? Well, I need to find the vertex. So we had the area is x times 50 minus x, and I want to rewrite that in this form ax squared plus bx plus c. So I just want to distribute the x across. And now I do have a quadratic function. Let me rewrite it. This is a quadratic function. It is a parabola. The coefficient on the x squared is -1. So it's a parabola that opens down. So it does have a maximum value. And that maximum value is going to occur at its vertex. So I need to find the vertex. All right, so we're going to first find minus b over 2a. So a is equal to -1. B is equal to 50. Let's make those substitutions. And we get 25. So the maximum length of this rectangle, the length of this rectangle to maximize the area would be 25. So what maximizes the area? For it to be a square. Okay, so what is the maximum area? Well, you could evaluate the function. at 25, or you could multiply 25 by 25. And what do you get? You get that the maximum area is 625 square yards. And area is measured in square units. So in this case, it's square yards because we were given 100 yards of fencing to fence in this area. All right, and that is the end of section 3.1.